All right, so this is part 2. We're going to be doing some calculations here, but before I get into calculations, I'm going to set the stage for the normal force. There are 3 different scenarios for a normal force on a flat surface. So 3 different cases for normal force. Remember our equation is me times the normal force. So the coefficient of friction times the normal force. Normal force is very important in this case, and it's not always equal to the weight. And I'm going to show you those 3 different scenarios. Right? There's 3 cases. So case 1 is the case at which I have, they're all flat surfaces. I'm going to write that in here, flat surfaces or surface. Case number 1 is where I have my surface and my object, and I'm going to push on the object parallel So I'm going to push on this object parallel to the ground. So we would say an applied force to the right. Now in this case, I'm not doing anything different to the normal force or the weight. So our weight force is going to be equal but opposite our normal force. So when you are applying a force to the right, your normal force will be equal to the magnitude, remember magnitude, of the weight force. How do we calculate weight again? We take the mass times negative 9.8. So that's case number 1. Now let's say that this is carpet that we're pushing the box on. Carpet in the box is kind of, depending on how massive the box is, this might be hard to do. So to make it easier, I'm going to take the box and I'm going to lift up the box a little bit. So I'm going to pull it up. So I'm lifting up. These are not force vectors. I'm just showing you the direction I'm pulling. So we're lifting up. So applied force is in the y direction. So we're lifting both up and right. So that's our case here. Now I'm on carpet, so if I lift up a little bit, what do? I decrease the contact here. I minimize the contact between the normal force and the box. So my weight force is going to be the same as it was in the first picture because the weight of the box doesn't change. What changes is my normal force. I actually minimize the surface contact. So in this particular case, my normal force, the magnitude of my normal force is actually going to be smaller than the magnitude of my weight force. Now weight again is still the same in both pictures. We still calculate weight the exact same way. It's still equal to mass times negative 9.8. So that didn't change. What changes is my normal force. Okay, and I'm going to explain to you how you find the normal force on a later lesson, okay? All right, so there is your case 1 and case 2. Now we're going to move on to case 3. So I have this box, I'm trying to move it on carpet, and I am kind of feeling tired and lazy. So I start to lean on the box and push it. I'm super tired, super lazy. And so I'm going to lean on this box. So instead of lifting up, maybe my back is a little sore. I'm going to lean on the box. So I'm pushing out and down. So my applied force is down and right. The box is still moving. It's probably moving a little slower, as you can imagine. The box is still the same size, so the weight is still the same in this case. But because I am increasing the surface pressure, I'm increasing the contact here. I'm increasing that contact. My normal force is going to actually increase. So the magnitude of my normal force is actually going to be a lot bigger than the magnitude of the weight. And again, you calculate weight the exact same way. Mass times negative 9.8. So the weight in all 3 cases never changed. Now, of these 3 methods, which method is the best method if I want to move something from one side of the room to the other? Should I push parallel to the ground? Should I lift up on the object and pull? Or should I lean down on the object and push? Well, whatever is going to minimize the normal force is the answer here. So I'm going to minimize my normal force by lifting up. So this is case 2 is the best method to moving an object.